to Coffee Break with Microchip Technology. Coffee Break is our ongoing forum in which we talk about new and evolving technologies, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Glatfelter. Joining us today is Aaliyah Fahout, our moderator. Welcome back, Aaliyah.
Thanks, Eric, and thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and you can participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after the broadcast. Don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Eric.
Thanks, Aaliyah. Our topic today is strategies for making fan control a breeze. We have two folks in the studio with us, Senior Product Marketing Manager Mitch Polonsky and Applications Engineer Josh Booth. Welcome to you both.
Thanks, Eric.
All right, so let's dive into fan control. Before we do that, let's kind of go into some of the nuances. What are we talking about? How does the fan control market divide up, and help us understand some of the differences there?
Sure, I'll take that, Eric. So basically, when we talk about fan control, there is, we want to distinguish the fact that we're not going to be talking about motor control itself. We're going to be talking about controlling the fan and strategies associated with that and what we have there. We're also going to be more specifically talking about DC brushless fan control. There is the older brush motor control, and that's less popular now just due to wear and tear. And so most of the fan control strategy that our audience needs to know is about DC fan control.
So most of the designs today are brushless DC fan control?
Yes, that's right.
Okay, so what are the most common applications for that technology?
So brushless DC fans can be found a ton of places nowadays. With the revolution of EV charging, there's a lot of power-hungry electronics in there that are pumping a lot of current, and so those can't be passively dissipated, so you're going to need an active fan in there. So for every design for EV chargers, you're going to need brushless DC motor to keep electronics cool. So in the automotive space, there's a lot of need, as well as applications like industrial. So anywhere that has networking equipment, PC server racks, anywhere that just needs cooled with a lot of power, brushless DC fans are a great application. And you pretty much interact with them or interact with something that is passively and actively cooled every single day.
Okay, now that's a pretty broad range of applications. So if you're talking about industrial or servers or things like that, it seems like you may actually have a very large physical space, but tons and tons of energy that's being dissipated. Something in an automobile, it may be a lot less power, but the space may be much more constrained, and you might have more challenges with thermal dynamics.
Exactly.
Is that true? Is that a true statement? Okay. So, so these strategies can help us, or these products and solutions can help us with all of those different applications.
For sure.
Okay. All right, so let's start talking about some of the design challenges in this space.
Okay. Up front, I'll add on to what Eric mentioned, and there's also the fan controllers that are inside your PC, that sort of thing, right? So we do vary a lot in the sizes of these applications. But there's some common challenges, regardless of the size. Let's start with the challenges and the technologies that we have to assist on those challenges, right? So we have fan aging, right? So first of all, we know that fans are mechanical in nature, and sometimes dust gets in the fan. So over time, we need to be cognizant of that. And so we have the ability to check on whether we're meeting the target fan speed and being able to alert if the fan's aging. Another thing that we have in terms of technologies is for acoustics, right? So for acoustics, we all know that some of our fans are just bothersome in our PCs, things like that, and we're always wondering why. Some of the technologies to address that has to do with ramp rate control, right? So we don't want to go from 0 to 100% fan speed, because that's when we really hear and get that acoustic annoyance. And then lastly, we want to keep it outside of the acoustic range, which is about 20 kilohertz for the human ear. Okay. Moving down the list, we have startup, and we need technologies to get over the inertia of the actual motor itself, right? Because we are talking about controlling a motor. And so we've got some programmable algorithms built in that we can rely on. Again, moving down the list, we've got locked rotor. That's pretty obvious, right? We want the fan to move. But lastly, it's nice for everybody to know that we actually have some fan controller ICs that integrate the temperature sensor and help us set both temperature and fan speed in conjunction and have a closed loop algorithm.
Okay, so you can monitor the actual temperature that you're getting and adjust the fan speed accordingly to accommodate for being over or under the target.
Exactly.
Okay.
Exactly.
Okay,
Yeah.
great. So we've got dedicated from a hardware perspective, we've got dedicated fan controller ICs, and we also have MCUs that have peripherals with some fan control capabilities built in. So help us understand what are the pros and cons of each one. So let's start with the dedicated fan controller ICs. Where do those excel?
Okay, so that's my side of the Venn diagram. So we're going to go and use a Venn diagram that we post on the screen. And so for a dedicated fan controller IC, we have some built-in algorithms that I referred to earlier, right? We want to minimize the annoying acoustics, and so we use what we call ramp rate control, right, to slowly ramp up the speed so that it's not as noticeable. Also, we have the temperature sensor built in, right, so we can have some automatic temperature measurement and fan control going at the same time. We also have that going in a closed loop fashion, so not only do we set the fan speed, but we also check to make sure that we make it to that target fan speed. And then just kind of going down the list, we've got a nice benefit of just time to market, right? This is a fan controller IC, has a lot of built-in algorithms, and that's an advantage in and of itself.
Okay.
Now I'm going to leave it over to Josh, who knows what the microcontroller is going to bring to the party.
Great. So where do those excel?
Yeah, so, and for the fan control ICs versus a microcontroller, it's all about picking the right tool for the job for your application when you're trying to solve, depending on what challenge you have, like we presented on the previous slide, depending on what's important to you. So from a microcontroller perspective, it's just a little different paradigm. We have these core-dependent peripherals that can drive the fans, but then you just have a general purpose CPU controlling all of them. So you're going to have to do some software development in the beginning of your application, which you wouldn't have to do with the ICs. Right. But the pro to that is then you get a lot more flexibility and customization. So if you want a custom fan control ramp rate algorithm or temperature compensation algorithm, the ball is in your court to design what you need for your specific application, and you get that additional flexibility. Okay. Also, because you have that general purpose CPU, you can still use the microcontroller for other system functionality, such as monitoring I/O, controlling different aspects that aren't related to the fan, since the fan control could be segmented to those core independent peripherals. Also, that can kind of give you some BOM consolidation. If you needed a microcontroller, you're just having one piece of silicon on your design instead of needing an IC and a microcontroller.
Right.
Okay. Right. So a lot of this choice may come down to your overall system complexity and whether you need an MCU for other things as well.
Right.
Right.
Okay. All right. So great from a hardware perspective. Obviously, there's tools and software involved. So again, help us understand kind of the design flow for each one of these. Let's go back to the fan controller ICs.
Sure. So if we back up like 10,000 feet again, in terms of the benefits under the umbrella, we've got time to market, right? Because we've got these built-in algorithms, and that makes it a lot easier to set up the fan control and take that thing to market for your end application. Another element, though, within the time to market are those algorithms, right? So again, built-in ramp rate control to lower the acoustics, right? And so we've got some certain set points to make it a little bit easier. You don't have to think about what your settings are off the top of your head. And then also your startup, right? We're overcoming the inertia of the motor, and we've got some built-in setup configurations for that. Moving down the list, something a little bit more subtle is being able to put your entire system to sleep, right? So basically, we have a fan controller IC, and it's going to run that fan control, once you set it, you can forget it, right? And it's gonna go and work, and the rest of your system can actually be put to sleep. So if you want your entire system to sleep while the fan control runs, you can wait for that alert from the fan controller IC, so that's good. And then lastly in the list of things to consider for a fan controller IC, also something that's a little bit more subtle, and that's your division of labor and what you're comfortable with in terms of design, right? So some companies and engineers are more comfortable with hardware design, some are more comfortable with software design, and there's a division of labor that you need to figure out what's best for you and your design team. And so with a fan controller IC, you've got benefits on the hardware side for the people that are a little bit more comfortable with hardware engineers and setting up their system that way. We've got some algorithms, as we mentioned, and that's easier for a hardware engineer taking his system to market. So now I'm going to pass it over to microcontrollers.
Back over to Josh from MCUs. Yeah. What's the design flow look like there?
Well, so you get that flexibility that comes with the programmability, but that requires the initial software development time in the beginning, unlike what you would have for the IC. Now, that does take an initial startup, but we at Microchip are hoping to make that process as small as possible for you by providing all the resources and tools you need to get up and running quickly. So, and then you can utilize the BOM consolidation in your final design. So we have a MPLabX IDE, so that's a universal IDE for all of our PIC and AVR microcontrollers to program them, as well as a Microchip code configurator. That's a graphical tool for configuring these core-dependent peripherals so that you can use your CPU for other tasks on your system. And then we also have a GitHub repository of Microchip PIC and AVR examples full of possible ways that you can use our microcontrollers. And then this provides full application examples that you can just copy and paste the code directly into your final product so that we can minimize that initial software development time.
Awesome. So it sounds like there's, you mentioned reference code and code examples. Are there hardware reference designs as well?
Yeah, for sure. So we're going to flash a QR code, and on this QR code we've got a list of 10 resources, videos, right? We've got a video series in terms of if you're new to this topic matter for fan control IC. We've got a video series. We've got reference designs, whether you're designing the fan controller IC reference design. We've got a couple of those in there for single fan controllers, dual fan controllers. We've got also a reference design for the PIC AVR. We've got a reference design also for a ceiling fan. So if you're specifically doing a ceiling fan, we've got everything you need to know there. And then lastly, we obviously have evaluation boards. All this can be found when you hit that QR code.
All right. Excellent. Thanks for the overview. Thanks for the page with all the information so people can get started. At this point, let's go to Aaliyah and see if we have questions from the viewers today.
Yes, Eric, we do have a few questions. This one is coming from YouTube. It is, can acoustic be used to control fan speed somehow, or is acoustic primarily used to find if the motor is in good condition?
Okay, so the question again, can acoustic be controlled? So we don't have a system that uses the actual, an actual microphone to make sure that your acoustics are going well. There are some labs that specialize in that, where you can bring a fan into a lab to examine the acoustics and see what the results are. But Microchip doesn't do that specifically, and we don't have a specific setup for that. But it is a good question, and I'm sure it's a question that a lot of people have.
Well, so to piggyback on that answer, if you're looking to use acoustics for fan lifespan and determining, we don't have something for acoustics, but on this resources page, we have an example that measures the vibrations to check the longevity of your fan using some machine learning setup.
Okay, awesome.
All right, that's good.
Awesome. And we have machine learning tools for the 8-bit MCUs.
Yeah, there's a repository that goes through how to set it up and how to replicate that example in your own.
Excellent. Okay. All right.
Aaliyah, anything else?
Yes, thank you both. Another question from YouTube is, fan control IC algorithms are typically digital state machine paradigm or digital signal processing. Can this be applied here too?
For the fan controller IC, it is a state machine, so it's not digital signal processing. We just have gone through a lot of different state machine setup parameters that make it easy in terms of knowing basically what duty cycle I want to start the fan at and how long I want the kickstart to be, and that sort of thing, but not DSP for the fan controller IC.
Great, thanks, Mitch. Another question for you is, what is the accuracy of the fan controller ICs?
That's a good one. I'll take that one. So the fan control IC has a 0.5% accuracy, and that refers back to the RPM control. So if you're designing and you want control of your RPM anywhere from 500 hertz all the way up to 16,000 hertz, you can have that, RPM, 16,000 RPM, you can have that control. Oh, it was hertz, sorry. All right.
All right, thanks, Mitch. Another question for you. Are there software solutions for MCU fan control like SDK or library, which does not require external ICs?
So I would recommend going to that GitHub pick an AVR examples repository and searching fan control. Off the top of my head, we don't have a all-encompassing fan control solution of something for just getting up and running like that, but we do have a lot of development boards and how to drive a fan with our microcontrollers, and that you would be able to quickly check and see if that paradigm will work for your development.
Great, thanks, Josh. Another question for you is, what's the best way to start an MCU fan control design?
Yeah, so kind of once again goes back to getting our evaluation board. So that's a Curiosity Nano. All you need is a USB cable to get the microcontroller programmed. It includes an integrated programmer. Then I would just pick up an off-the-shelf brushless DC motor that operates at 5 or 12 volts, and then you can start driving it with PWM and start playing around with our toolchain. After you get started there, the ball is in your court with the functionality. Once you know how to drive the fan with our microcontrollers that is covered in the GitHub pick an AVR examples repo, you can then do the custom ramp rate control, custom temperature compensation, and that's sort of the path I would take.
Great, thanks, Josh. Another question is, to overcome the inertia of the motor, what does a function like startup algorithm do?
Okay, so in terms of the fan controller ICs, again, we're overcoming the inertia of the motor, and so we need a kickstart of sorts. And so to do that kickstart, what the algorithm has is the ability to define how long the kickstart will be, how long the startup will be, anywhere from 250 milliseconds all the way up to 2 seconds. And within that 2-second period, you can define whether you want to kickstart at 100% of the full fan speed a quarter of the time, right? So let's say we're talking again 2 seconds, so for a half a second you can have it go full speed on, and then for the other 3/4 of the time you would define what your duty cycle is, that is your on-off duty cycle, anywhere from 35% up to 60% duty cycle.
Great, thank you. Another question for you. I think we could do a couple more. Would a PIC or AVR microcontroller be better at fan control?
Ooh. So PIC and AVR, they both have their strengths. For fan control, I would I would say go to there's a fan control IC page we have on our website that highlights the features that each PIC and AVR has, and I would pick the one that's better suited for your application. I know on that page we have the PIC 18 Q24. If you need any MVIO multi-voltage level shifting in your application, that would be a great one because it has multiple timers and multiple PWMs. A great alternative in the AVR space would be the AVR DD. That might hit a better price point at the end of your design, but it might not have all of the features that you're looking for. I would just go and see what you need and then browse that page.
Great, thanks, Josh. Here's the last question I have for you, and it seems like a fun question. Why are some fans so noisy?
Okay, I'll take that. So well, first of all, it is a mechanical device, so there is some onus on the fan you choose, but outside of the fan you choose, we are talking about basically a duty cycle of on-off behavior. And so if you're doing it at a low frequency, let's say it is going on for a second, off for a second, you're going to notice that, right? And so that's when we get into, we want an acoustic frequency above the hearing audible range, right? And so that's about 20 kilohertz. So if you're above 20 kilohertz or above, you're not going to get that on-off audible noisiness. So that's one of the reasons. And the other reason is the ramp rate control, meaning that, again, and going a little bit back to on-off, if I go from 0 to 100% on, I notice that I go from complete quiet to I hear the fan go on. So we want to slowly ramp up that speed and minimize the acoustics. So ramp rate control, bad ramp control would be noisy, and also audible frequency range. If you're below that audible frequency range of PWM drive, that's going to create annoyance.
Great. Thank you, Mitch, and thank you, Josh, for answering the questions. And for our viewers, if you have additional questions or comments, you can email us at livestream@microchip.com. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you guys.
Thanks, Aaliyah. I'm happy to report that my PC is not making any acoustic noise at this moment. So thanks, Aaliyah.
Control.
Thank you, Josh and Mitch, for sharing your expertise here. Thank you to our audience for taking some time out and listening in to Coffee Break today. Please visit us at microchip.com/coffeebreak. There you can see our upcoming sessions from now until the end of the year. You can put them onto your calendar, you can sign up for notifications, and you can also peruse our library of previously recorded sessions. So thanks for joining us. We hope to see you next time. See you then.